Hello and welcome to this video where today we're looking at the mass and the energy changes inside nuclei of atoms. Now before we do that, there's a couple of definitions that we need to know. So we're going to be looking at how masses change inside nuclei when we take nuclei apart. So we're going to define a different unit of mass just because it's easier to work with, because we're going to be, otherwise we'll be working with really small numbers like 10 to the minus 27, 10 to the minus 28 kilograms, that sort of thing. So we're going to define this atomic mass unit. It's given the symbol U, and it's defined as 1/12 the mass of an atom of carbon-12. So basically, if you take one atom of carbon-12, you find the mass of it. If you then divide it by 12, that would then give you in kilograms the mass of one atomic mass unit. So 1 U is equivalent to this many kilograms. So if we actually took our atom of carbon-12 divided by 12, this is how many kilograms we'd get. So that's our definition of the atomic mass unit. We can express different masses in terms of this atomic mass unit. So if we basically take the mass of a proton, and in terms of the atomic mass unit, it's simply given by this. And if we take the mass of a neutron, it's given by this. And you can see that basically they've got the same, within 2 decimal places, they've basically got the same mass. However, we're going to be looking at really small masses and really small differences in mass, so we're going to keep many more decimal places than we would do normally. So these two numbers are going to be quite important. You don't have to remember those, they're on your data sheet. Also, what we're going to look at is we're going to look at the equivalence between mass and energy. Now we know, and you've met before, that Einstein said that E equals mc squared, so which we're going to have a look at in a second because it'll help us make some sense of some things that's going on. But if you can convert mass into energy and vice versa. If we converted one atomic mass unit of mass completely into energy, then that would be equivalent to 931.5 MeV. The reason that we're going to be using this conversion unit is because if we want to convert masses into energies, the only way that I could do that if I didn't know this conversion unit, this conversion would be to take this atomic mass unit, convert it back into kilograms, then put that into E equals mc squared, which would give me an energy in joules. Then I have to take my joules and put it into electron volts, and then finally into MeV. So there's lots of steps there. Simply by using this, which is on your data sheet, means that you can do the conversion from an atomic mass unit to MeV just really straightforwardly. So let's have a look at what happens when we basically make a nucleus. So what we're going to do is we're going to think about this. We're going to think we've got 2 protons and 2 neutrons, and we're going to put them together, and we're going to make a helium nucleus like this. And we're simply going to have a look to see what happens when we compare the mass of these 4 things to the mass of this thing, which is made up of these 4 things. Well, your common sense would say, well, the mass of that and the mass of that are the same. So let's see. So this is the mass of a proton, this is the mass of a neutron. So I can work out the total mass here, because the total mass is simply 2 lots the mass of the proton, because I've got 2 of those, plus 2 lots the mass of our neutron. And if we do that, and we use these numbers, well, 2 lots of protons, or 2 lots of this thing, 1.00728, plus 2 lots of the mass of a neutron. So 2 lots of this one, 1.00867, and if I calculate that, I get 4.0319 atomic mass units. So that's basically the mass of these 4 things. So that's what you'd expect the mass of this thing to be. However, that's not actually true. When you actually measure this thing, then the mass of a helium nucleus is 4.0024 atomic mass units. So there's something weird happened. The mass of these 4 things is greater than the mass of this thing. Now this is called the mass defect. So the mass defect is, you can calculate, and is basically the difference between this number and this number. So we can calculate the mass defect for this thing simply by doing 4.0319 minus 4.0024, and if we do that, we get our mass defect is 0.0295 atomic mass units. So that tells us the difference in the masses. So that's a bit strange. What we want to do is we want to kind of come up with an explanation of why this happens. So again, we have to go back to our Einstein type of thing, because we know that energy and mass are related. So that if we gain energy, that's the equivalent of gaining mass, and if we lose energy, that's the equivalent of losing mass. And exactly the opposite happens. If we actually gain mass, then we gain in energy, for example. So if we look at this, basically what's happening is because we're kind of losing, we're not, in a sense, we're losing mass between here and here. What's happening is the energy between here and here is going down. So what's really happening is this: when these things are they're fairly close together like this, there's a potential energy between them. So if we take our two neutrons, because it's not complicated by the fact that they're charged, when they're fairly close together, the strong nuclear force is wanting to pull them apart. So there's some potential energy between them. You can kind of think of this as, so if you go for an everyday explanation, let's imagine that, before we come back to this, let's imagine we've got our ground here. Let's imagine you've got the ground. And let's imagine you're holding up your pen up here. Now, there's obviously, your pen has got gravitational potential energy because it's raised off the ground. If you let it go, it'll fall down and that gravitational potential energy will go down. So it's actually got greater energy up here. So there's more energy up here than there is down here. So that's got greater energy. When it falls to the floor, the energy's gone down. If the energy goes down, actually technically what's happening is the mass has gone down. But obviously for us, for a pen, we're not going to see that at all. However, for these things, because they've got such small masses, then we potentially could notice that change. So we've got this potential energy between them, just like we've got potential energy between these two. The closer they get, the smaller that potential energy is, until they get really close together, and that potential energy is basically gone. So they have less energy, and if they've got less energy, they've got less mass. So if you join these things together, then because there's less energy, there's less mass. So the mass of these four things joined together is less than the mass of these things. So that's basically what the mass defect is. There is a difference in mass because there's a difference in energy. And this difference in energy is called the binding energy of a nucleus. Now this is slightly confusing because the definition for the binding energy is exactly the opposite that you think it's going to be. So let's kind of run this in reverse. Let's imagine we've got this nucleus and we want to separate it out into these four constituents. What I'm going to have to do is I'm going to have to basically take this one and I'm going to have to put some energy in and give it some energy to pull it apart. Because there's an attractive force here with a strong nuclear force, when I pull it apart, I'm giving it energy. And when I give it energy to move it away, because it's got greater energy, it's got greater mass. So therefore that gains a bit of mass. If I then want to take this one away, I've got to add some energy to that one, and so that gains some mass. And to split these two up, I've got to add some energy to these two. And so what I've had to do is I've had to put energy into this nucleus in order to separate the thing out. And by putting this energy in means that the energy of the system and therefore the mass of these things have gone up. So the binding energy is actually related to the amount of energy it's required to actually split this nucleus up. And this is your definition of binding energy. It's simply the energy that's required to split this nucleus up into its individual nucleons. So this binding energy here is how much energy it takes to actually separate these four nucleons into just two protons and two neutrons that are far apart from each other. So it takes 27.5 MeV to do that for helium. So the kind of question you can be asked is something like this. So I want to know what the binding energy in MeV of this oxygen nucleus is. So I know the mass of a proton, I know the mass of a neutron from my data sheet. I'm given that the mass of this oxygen nucleus is this. So I need to follow these steps through just like we have done before. So first of all, I'm going to calculate the mass defect. So mass defect is basically the difference between the masses when these protons and neutrons are completely separate and the mass of my nucleus when they're together. So if you look at this, I've got 8 protons because that's that number here. I've got 16 minus 8, so 16 minus 8 gives me the number of neutrons, so I've got 8 neutrons. So my mass defect is simply, I've got 8 lots of the proton mass, 8 lots of the neutron mass, take away this thing here. So I'm going to write it out all together. So I've got 8 lots of protons, so I've got 8 lots of 1.00728. And I've got 8 lots of neutrons, so 8 lots of 1.00867, So that would be the total mass of my individual protons and neutrons, and then I'm going to take away the mass of the oxygen nucleus, which is this thing here. So 15.994915. And if I do that, my mass defect, which I'm going to write as delta M, is given by 0.132685 atomic mass units. So that's my mass defect. However, I've not answered the question yet because the question wants a binding energy. So number 2, I'm simply going to use that conversion unit that I had before. Well, I know that 1 atomic mass unit is 931.5 MeV. So this is my mass defect. So if I just multiply this by 931.5, it'll tell me the binding energy of this oxygen nucleus. So my energy is equal to 0.132685, the number I've just worked out, multiplied by this conversion factor, and if I do that, my energy is equal to just 3 significant figures, 124 MeV. So what this tells me is I'm going to have to do 124 MeV of work. I'm going to have to put 124 MeV of energy in to this oxygen nucleus to separate all of the protons and neutrons inside this nucleus, and so they're all individual, they're all separate. So that's how this is a very, very typical question. It would be worth potentially 3 or 4 marks in an exam. So if we go back to this, what this basically tells me is how much energy I need to put in order to separate the thing out. And if we then go back to this thing, if you think about it, the greater the binding energy is for a nucleus, the more stable it is. Because if I know that, for example, it takes me a very small amount of energy to take these nucleons apart, then what that basically means is there's not a very big kind of force holding them together. So therefore it's easy to take them apart because the nucleus isn't particularly stable. The bigger the binding energy is, the bigger, the stronger that these things are holding onto each other, and therefore the more stable they are. Now, obviously, comparing the binding energy of helium-oxygen is not really fair because it's not valid because helium's only got 4 protons and neutrons, whereas oxygen's got 16. So you would expect the total binding energy of oxygen to be bigger simply because there are more kind of protons and neutrons to actually remove. So a more valid way of actually looking at this is to look at the binding energy per nucleon. So if we know the total binding energy of helium, we know there are 2 protons and neutrons, so there are 4 nucleons altogether. So if I do this number divided by 4, I get 6.9 MeV. So there's 6.9 MeV of binding energy per nucleon on average. So in other words, it takes me on average 6.9 MeV of energy to remove 1 nucleon from this helium nucleus. Sorry. For oxygen, I can do the same thing. I know there are 16 nucleons. I know the total binding energy was that. So therefore, I end up with a binding energy per nucleon of 7.8 MeV. So oxygen is more stable than helium because I have to put more energy in to remove these protons and neutrons than I do for helium. And so I can see that that's more stable than that. So helium is less stable than oxygen because it requires less energy to take the thing out. Now I can basically go in and I can look at that for every single different isotope of each different element. And if I do this, I can plot a graph that looks like this. So this is the mass number along the bottom. It's the total number of protons and neutrons in our nucleus. And this is the binding energy per nucleon. So it's not the total binding energy, it's the binding energy per nucleon in MeV. So the graph looks like this. So if I went away and did all of the experiments, I would plot a graph that looks approximately like this. If you go online and you have a look at the actual real graph for this, you'll see it's kind of the points are all over the place, but they follow this basic trend, and this basic trend is the thing that you need to know for your exam. So basically, for small nuclei, the binding energy per nucleon increases up to a maximum, and then as you get to bigger and bigger nuclei, the binding energy goes down. So what we said about stability, this thing here, this nucleus that's up here, this is the most stable. So that's the most stable nucleus we can get because the binding energy per nucleon is so big. So we have to put lots of energy in to kind of take it apart. Further down here, the binding energy per nucleon is less. So these are less stable. These things here and here are less stable than this is. So the things you need to remember for your exam, because you can be expected to draw this, basically you'll be expected to potentially add these numbers to this axis, and you're expected to know that the peak, this peak up here, happens at approximately 8.7 MeV. So you'd get a mark for knowing this particular number, and then you'd also get a mark for putting in the correct unit. Often the unit would be missing from here and you'd have to add it in. You'd also have to know that this peak happens when the mass number is approximately 56. So that gives us a nucleus of about iron. So that's your third mark, one for that number, one for adding this unit, one for the correct mass number, and then finally this then goes down, but it doesn't go kind of back down here. It just falls gently, and you'd have to make sure that the total fall that you draw, isn't more than a third above the peak. So if the peak's approximately 9, you don't want to go down below 6, and this one doesn't, so that's okay. So you can see from this that iron is the most stable element because it has the greatest binding energy per nucleon, and iron in that case also has the greatest mass defect, because big mass defect basically means that the binding energy will be bigger. One last thing to mention is very often you can put this graph and these kind of calculations together. So for example, we know that the mass number of iron is 56, and we know that the peak is 8.7 MeV. So if you wanted to know the total binding energy for that particular nucleus, then you know that the mass number is 56, so the total number of nucleons is 56. You know that the binding energy per nucleon is 8.7. So to work out the total binding energy of that nucleus, you simply multiply these two together, and it tells you the total amount of energy that is needed to take that iron nucleus apart. So in this video, we've had a really quick look at basically the changes in mass and energy in a nucleus when you're basically trying to take it apart. We defined the atomic mass unit, which you need to know. We also defined the binding energy of a nucleus, which again you need to know, and you need to basically just be able to write down. We had a look at how you calculate the binding energy just by looking at the mass defect of the individual nucleons and that of a nucleus. And then finally looked at this particular graph. So they're the main things that you need to know for this topic. In the next video, we'll have a look at how this graph relates to nuclear fission and to nuclear fusion. But for now, thank you very much for watching, and I hope to see you again soon.